So last time we talked about catalysts and their basic properties. We saw that a catalyst is something that speeds up a chemical reaction but doesn't change its thermodynamics. It's something that's added to the reactant side but also reappears over on the product side, or at least that's one way to understand it. And so because it appears on both sides of the reaction, it doesn't change any of the thermodynamics, doesn't change equilibrium constants or delta G's or anything else. But it can accelerate the rates of reaction by huge amounts in some cases. We saw that we can understand how a catalyst works by thinking that of the fact that it lowers the activation barrier, it binds to the transition state, and stabilizes the transition state, and that thereby lowers the activation barrier, and that explains why it speeds up both the forward and the reverse reaction for an elementary reaction by the same amount. And therefore, since the K forward over K reverse is the equilibrium constant and they're both sped up by the same factor, it doesn't change the equilibrium constant, and in the same way it doesn't change anything else. Before we go on to enzyme kinetics, which is what's coming, the Michaelis-Menten kinetics specifically, let's look at a couple of examples of how catalysts might work. So the example I've set up here is for an inhomogeneous catalyst. There are homogeneous catalysts and inhomogeneous catalysts. Inhomogeneous catalysts are powders, basically, or things with a solid surface. And stuff happens on that solid surface. Basically, the molecules in solution bind to the solid surface, and as a result of that, the surface can act as a catalyst to speed the reaction up. Homogeneous catalysts, on the other hand, are things that are already in solution. They don't have a solid surface, and so they work by different types of mechanisms. The chemical reaction I'm going to consider is our standard one, 2H2 plus O2 goes to 2H2O, but this time in the presence of a platinum catalyst. And let me give a caveat right at the beginning. I don't know whether the mechanism I'm going to show here is really right or not. I just made it up, in fact. It's plausible, but these kinds of things get researched for decades sometimes. It's very difficult sometimes to tell what's really going on, how a catalyst actually works. There's lots of research behind it. I probably could look it up if I wanted to, but for our purposes, this will do. So let's suppose we have some H2 in the presence of a solid platinum particle of some kind. Sometimes the particles are very small, very microscopic. You've got to look at them in an electron microscope. Not even a light microscope is powerful enough to see them, but it doesn't matter. They're still huge compared to the molecules in question. And so they represent a solid surface. Let's suppose the H2 binds to the platinum as an H2 molecule. And the reason why platinum works as a catalyst a lot is because it doesn't really react itself. It's pretty inert, right? It's like gold. But it still can stick to the molecules, and that sticking can weaken the molecular bonds. And so in this case, the H2 molecule comes apart into two hydrogen atoms. And because the hydrogen atoms are stuck to the platinum atoms in the surface, they're happier. They're forming partial bonds to the platinum surface itself. Not real strong bonds. In fact, they can't be real strong, right? Because the platinum's got to let them go at the end. A catalyst is oftentimes a subtle thing. It has to bind at some points, but it also has to let go at other points. And it's got to weaken bonds and so on. So a catalyst is a fairly subtle thing in a lot of cases. Platinum isn't anything that anybody designed, of course. It's just something that's been discovered to act as a catalyst. And there's a lot of things like that. So, all right, the first step is the H2 binds. Then the bond between the two H atoms breaks, and then the H atoms become loose H atoms on the surface, and they can probably run around. I mean, in a lot of cases that's true. I don't know for sure if it's true for hydrogen on platinum, but it probably is. When the hydrogen binds, the platinum atoms have a spacing. You can see the way I've drawn them here. that's a little bit larger than the spacing between the H atoms in the hydrogen molecule, and so it puts a little bit of a strain on the bond, and that helps to make it favorable for the H atoms to separate it, to separate into separate atoms. Let me say that there's probably an equilibrium between these two. In other words, some of the H and also an equilibrium with the gas phase, the molecules in the gas phase. So all these things are coming on and coming off all the time. And I'll bet that it's only a small fraction of the hydrogen molecules that actually break apart into hydrogen atoms at any one time. But that means there's a population of these guys around, and that's enough. Then let's suppose that an O2 molecule comes around. So there's a mixture of H2 and O2 up here. And it sticks to the surface, and maybe the O2s break apart also, but it isn't necessary. Let's suppose the hydrogen is free to move or hop from site to site along the platinum surface, and so it can encounter the oxygen molecule, and then it can cause a reaction like this, right? Now the hydrogen can bind to this oxygen atom, and they're both bound to the surface, and so you can get two OH radicals also bound to the platinum surface. Now let me point out, these things that we're talking about, loose H atoms and now loose OH radicals, those are the intermediates in the mechanism that we talked about earlier. Those are the high energy things that cause the reaction to go slow. So this binding to the surface that we're seeing here between the hydrogen and the platinum, that's binding, in this case, to a reactive intermediate to something that can be thought of as at least part or effectively acting as a transition state. So this is when you say that something binds to the transition state and therefore stabilizes the transition state and lowers the kinetic barrier, sometimes that actually occurs in ways that isn't instantly apparent at first, and this is an example of that. The fact that the platinum stabilizes these hydrogen atoms and also stabilizes these OH radicals later is a form of binding to something like a transition state and lowering the activation barrier. All right, next thing that happens is another hydrogen comes in, binds to this OH radical, or maybe it can even be that an H2 molecule comes down from solution and reacts with the OH radical. I'm not sure what happens, and these are the kinds of questions that have to be addressed experimentally, or else by some very high-powered theory. But the theory is usually not. It's not easy to do theory on systems this complicated. Anyway, the result is that you form water molecules, still stuck to the surface a little bit, but now because the water molecules are stable molecules in their own right, they're not stuck very strongly, and so they can release. And water molecules that have already formed, if they're out, and so if there's appreciable pressure of them up in the gas phase, they can come back down and so on. So there's an equilibrium here as well. But anyway, that's the result. And you can see that the platinum, if it's doing the things that I'm saying here, I mean, I don't know if they are, but if it's doing these kinds of things, would act as a catalyst. In the original mechanism that we talked about, it's down here, way down here. Here it is. Here's the original mechanism. Here's the platinum catalyzed mechanism, or parts of it. It's this step right here that's slow, right? You've got an H2 molecule. This is the thing that's determining the rate of everything after. Once you've got an appreciable concentration of loose H atoms, everything else happens fast. And so it's this spontaneous breaking of a hydrogen molecule bond. That's the slow step, because that bond is fairly strong, and there's not enough energy in surroundings usually to break that bond with any appreciable probability. So if the catalyst can come along and make it easier to break that bond, even by a relatively small amount, then it's going to speed up the reaction enormously, and so that's how that catalyst works. Yeah, that's what I was just saying here, actually. This is the slow step, and now it's much faster. And so this is the rate limiting step. Everything that happens afterwards happens fast. Yeah, lowering this one barrier vastly speeds up the whole reaction. All right, so that's an inhomogeneous catalyst. Let's talk about enzyme catalysts now. Enzymes are in solution. They're molecules along with the reactants and products in solution. So this is an homogeneous catalyst, or so it's considered to be. I mean, enzymes are big molecules, so in some ways it's a little bit like an inhomogeneous catalyst still. It's a very small particle for an inhomogeneous catalyst, but anyway, it's counted, they're usually counted as homogeneous catalysts. So what does an enzyme do? Well, there are various mechanisms, but one of the very most common ways that an enzyme works is that it binds to the transition state. Doesn't bind to the products, doesn't bind to the reactants very well. In fact, that's good because you've got to release the products at the end. But it does bind pretty well, or it's set up to bind pretty well to the transition state. Well, if you bind to the transition state, you're going to lower the energy of the transition state and therefore lower the barrier and speed up the reaction. So let's consider this example, this sort of just cartoon example. You've got some molecule that's A2 here. I've drawn it out in these pieces. And it's going to go to 2A, which means this bond is going to break. So you're going to get 2 of these N pieces. And let's suppose you have an enzyme that's got a pocket on its surface that looks like this. And that pocket looks like it could bind to the A2 molecule here. But suppose the distance here is, again, just a little bit bigger than this bond distance between the 2 halves of the A2 molecule. Then when the A2 molecule binds, it's going to stretch that bond a little bit. That basically provides or puts some energy in, some of the energy in that's necessary in order to eventually break that bond, and so stabilizes the transition state. Basically, this is the transition state. Stabilizes the transition state, makes the barrier lower, makes the reaction faster. Here's an example, a more concrete example of that kind of thing from an area I know from my own past research. And that's a DNA polymerase. I've just very schematically sketched out here the structure of the actual catalytic complex when a DNA polymerase is actually polymerizing a new DNA strand. And the way it works is the following. This gray stuff that I've filled in here, that's representing the protein. So there's a piece of protein over here that's holding, this is the DNA. This is the growing DNA down here. This is the template strand here, this one, this left-hand one. That's the thing that's getting copied. And this is the primer strand over here, as it's so called. This is the thing that's being polymerized, and it's got to do it in a way that the new genetic letters that are coming in read the sequence on the opposite strand and then get pasted into the growing strand. So what we need is a bond right there between the growing end of the primer strand and the new nucleotide, the new letter that's coming in. Well, how does that work? Well, you can kind of see that, I mean, I don't indicate it very well, and I'm not drawing all the complexity of the protein, but here's a part of the protein. It's stabilizing or holding in place this terminal base on the DNA. Then there's another part of the protein that's holding in place a divalent cation. Usually that's a magnesium. Sometimes it's other +2 charged cations as well, but magnesium is by far the most common from what I've seen anyway. And then there's a third part which plays the role of basically stacking. You can see I put some stacking groups in here on this base for the nucleotide, and therefore stabilizes the base and holds it in position 2. The net result is to hold this new nucleotide in exactly the the orientation and position that it needs to have so that the atom that it needs, these are phosphate groups here, they're not really single atoms, but I'm drawing them as single atoms. The atom that it needs to be near, that this guy, this alpha phosphate, needs to be near, is near and positioned with the right angle and everything, near the 3' OH group, that is the reactive growing end of the primer strand. So it can form this bond here. Now, what's going to stop the bond from forming? Well, it costs energy. You got to break this bond, right? And it costs energy to break that bond. And the transition state will be something where there's a partial bond between this guy will be partly broken and this guy will be partly formed, and that will represent the top of the energy hill in something like the transition state. How does the polymerase, the enzyme, the catalyst, stabilize that transition state? Well, here's how. When the transition state starts to form, charges build up on both the alpha phosphate here and the beta phosphate here. And so this +2 ion that's being held in place by groups in the protein, this magnesium ion, strongly interacts with these developing negative charges on the phosphate ions. And that stabilizes the formation, right? It costs you energy to form charge like that. It costs way less energy if there's another plus charge right next door to neutralize and interact favorably with the developing charges. And so this transition state has a much lower energy than a corresponding similar transition state would have in the absence of a protein. I'm going through this in part because you should see how these things look. I mean, same up here, right, with the platinum case. You should see how this very schematic picture that I've drawn here, for example, binding to the transition state, that's just a cartoon. It's very schematic. What does this really mean in real life? Well, it means something like this, yeah. An arrangement of atoms such that the transition state is more stable, happier, if you like, at lower energy than it would be if it were on its own. And the next result is, yes, the bond that you need forms, and the alpha phosphate goes away, and the new letter is stapled in place in the growing DNA. All right, so those are examples, sort of semi-concrete examples of what catalysts actually do. We also now have sort of the generic overall theory of what a catalyst does. Now let's talk specifically, let's return to our kinetic formalisms and talk specifically about the Michaelis-Menten mechanism. I think that a fair number of people in the class are already familiar with this. At least in the past that's happened. I have encountered many students who already know as much as I do about this mechanism. If that's true, well, that's great. This will be an easy section for you. All right, so when you put a catalyst in, as you can see from the examples above, what the catalyst does is change the mechanism. Catalyzed reactions have mechanisms, and they're different than the mechanism in the absence of the catalyst. So, for example, for a water-forming reaction, here's the mechanism that I also don't know if that's actually, I know for a fact that this mechanism isn't actually complete. But here's our simple version of a water-forming reaction mechanism in the gas phase in the absence of a catalyst. And going by the pictures I drew up above, here's something, or at least part of, all the steps that are present, all the elementary steps that are present in the presence of a catalyst. And I haven't even finished here, and I've already got 4 of them, and there's probably 4 or 5 more. So there's a lot more steps in the presence of a catalyst, of course, because the catalyst adds complexity to everything that's going on. And these mechanisms, I mean, in principle, we could write rate equations for these mechanisms, And we could analyze for how fast the reaction goes as a result of that mechanism and how it behaves on the presence of reactants and products. And so you can understand a catalyzed reaction using the same tools and ideas that you can use for any other reaction. A catalyzed reaction is a type of reaction, and the tools we've developed so far work for any reaction, so they'll work for that. For the Michaelis-Menten mechanism, here's the mechanism. The Michaelis-Menten theory, here's the mechanism. Let me say that the Michaelis-Menten mechanism, or things that behave according to Michaelis-Menten kinetics anyway, are extremely common. I guess I don't know what fraction of enzymes, never seen anyone try to estimate what fraction of enzymes obey Michaelis-Menten kinetics. I'm going to call Michaelis-Menten MM here. But it's probably pretty high. I'll bet it's might be as high as 80%. Most of the enzyme kinetic mechanisms that I've seen are Michaelis-Menten mechanisms or some variant of Michaelis-Menten. All right, so here's the mechanism. We have a substrate. The overall reaction is S goes to P with an enzyme present. So the mechanism is that the substrate S plus the enzyme E form an enzyme-substrate complex. That's the binding of the substrate to the enzyme, like in the example above. Then the enzyme-substrate complex can fall apart back to enzyme and substrate. So these first two steps are just forward and backward reaction for the binding of the enzyme to the substrate. Or alternatively, there's a branch here in this mechanism. The enzyme-substrate complex can form a product and then release that product, leaving behind an empty enzyme again. There's three rate constants, K1 for the binding, K-1 for the unbinding or dissociation, and K2 for the actual product formation. If I were to write this same three-step mechanism out as sort of a flow diagram so you can more easily see kind of what all these steps mean in terms of how things change, then it would look like this. E plus S with a reversible step goes to the intermediate enzyme-substrate complex, which then goes on to form enzyme plus product. It's important that this enzyme-substrate complex is an intermediate because we're going to be using the steady-state approximation in a minute. And for that, for the steady-state approximation, the intermediates are, of course, the key quantities or the key species involved. Let me get rid of some of this purple junk, this pink junk. You know, I really hate this pink color. I would like to use a different color. It's just that I tend to use those same colors in making the notes. The pink is distinct, so when I go through to clean it up later, I can tell what's new and what's not supposed to be there. Anyway, all right. So there's our mechanism. We can write rate equations from the mechanism for all the species involved. There are four species: the substrate itself, the enzyme-substrate complex, and the product. And these are the rate equations. I don't think there's too much to say about them. I won't try to analyze them directly this way. The only one that really matters for us is this one for the intermediate, right? Because we're going to use the steady-state approximation, which means setting that to 0. And this one for the formation of the product, because that's going to determine, that's our definition of the rate of reaction. What we mean by rate of reaction in this setting is the rate at which product is produced, P is produced. Notice, however, that the rate at which P is produced depends on this intermediate, the enzyme-substrate complex. And like always, when we have intermediates present, we're going to want to eliminate that from our overall rate law for the enzyme's catalyzed reaction. So we got to get rid of this ES. We're going to use the steady-state approximation. We also have one extra piece of information. We've got these rate equations, but we also have this conservation equation. The amount of the amount of enzyme never changes, which means that the total amount of free enzyme and the total concentration of enzyme substrate complex, that has to at all times equal the total amount of enzyme that we put in at the beginning before any reaction took place. So we will be able to use that also to our advantage. All right, now we're going to invoke the steady state approximation. We're going to say that the reaction has reached a stage where this enzyme substrate complex concentration stays pretty steady, and therefore its rate of change is nearly zero. That's an approximation, but a decent one, a good one, universally made. I have a comment up here that's worth pointing out. I don't normally talk about the history behind all these things, but in this case I guess I'll make a slight aside. The original Michaelis-Menten theory was derived, of course, by Michaelis and Menten in 1913 using something called the rapid equilibrium approximation. We haven't talked about that, but that basically means that they assumed that this step went forward and backward fast enough so that these guys were approximately in equilibrium with these guys, and that's true if this next step, the K2 step, the actual formation of product step, is slow compared to the binding and unbinding. And that's a fine thing to assume and gives you a sort of decent answer. But it's probably not true most of the time. And so later, in 1925, Briggs and Haldane rederived the Michaelis-Menten mechanism using the steady state approximation as we're doing it now. And that gives you a slightly different answer. The thing called Km, which I haven't defined yet, but which we will talk about as we go further, comes from the Briggs and Haldane derivation. When you use the rapid equilibrium approximation, you get a Kd there instead rather than a Km, and we'll see the difference between those two as we go along. All right, so here's our steady state approximation. We set this intermediate rate of change of the intermediate to 0. Just doing some algebra that allows us to solve for the enzyme substrate complex concentration, and just doing the algebra, that's K1 over K1, K minus 1 plus K2 times E times S. It is conventional to identify, this is a definition, right? Three bars on the equal sign there. To define the Km or Michaelis constant as K, it's 1 over this. It's K minus 1 plus K2 divided by K1. I have in green here, notice that these are both first order rate constants. The K1 down here, though, is a second order rate constant. So the units on the top are seconds to the minus 1. The units on the bottom are molar to the minus 1, seconds to the minus 1, which means that Km has units of molar. It's not really an equilibrium constant. It's a collection of fundamental elementary kinetic rate constants. But notice that if K2 here were 0, then this would be K minus 1 over K1, and that would make this a KD. So Km is oftentimes treated like a KD, like a dissociation constant. And in fact, if you make the rapid equilibrium approximation, which is what it amounts to say that this K2 is nearly 0, then you get KD out of the derivation naturally, and that's what Michaelis and Menten did originally in 1913. A lot of people talk about the Km value treated as if it were a KD in a lot of cases. You'll see that. That's an approximation. Sometimes it's a good one, sometimes it's not so good, but a lot of people do it. All right. Then in that case, we have that the enzyme substrate complex is equal to E times S divided by Km. Now we use this enzyme conservation relationship that we have. We want to get an expression for E in terms of E0. This ES is in the way, so we substitute our new relationship in. I substitute that into our conservation relationship. And now I can factor out the E and then divide through, well, let me just do the steps. It's E then times 1 plus S over Km is equal to E0. And now I can divide both sides by that, and that's what you get here. So the free enzyme concentration is equal to the total enzyme concentration divided by 1 plus S divided by Km. And plugging that back into the expression for ES. We want ES, right, because our rate of production, our rate of reaction is K2 times ES. We want to eliminate that from this rate law. And so going back up here to ES, I replace this E by this new expression that we have, and that gives that the enzyme substrate complex concentration is equal to the total enzyme concentration times S over Km over 1 plus S over Km. Now that goes down in here, and that gives us, and I make another definition, I say that Vmax is equal to K2 times E0. So yeah, that's here, that's Vmax. And so, putting everything together, we get our Michaelis-Menten rate law, which says that the rate of production of product is this quantity Vmax times S over Km. You'll often see it written this way, over 1 plus S over Km. You oftentimes see it written in other ways too. And that's the same thing, dividing top and bottom by S over Km as Vmax over 1 plus 1 over times 1 over 1 plus Km over S. All right. So again, I think many people are familiar with Michaelis-Menten rate law, this final result here. But I think it's probably less common that you've actually derived it, so I spent some time going through the derivation. Let me say that I'm not a kinetics guy, really, and so I haven't, especially not an enzyme kinetics guy, and so I haven't spent very much research time doing Michaelis-Menten kinds of stuff, but it still comes up all the time if you're in any kind of biologically related field. Michaelis-Menten is going to come up. And then remembering this derivation and how it comes about helps clarify exactly what Michaelis-Menten means and when it's good and when it's not and so on. It's very helpful. So I've spent some time on it for our purposes. All right. So that's our Michaelis-Menten rate law. Now let's see if we can understand what it's telling us about how this enzyme, about how a Michaelis-Menten enzyme works. First, a couple of remarks. First of all, it's from the way we've done this derivation, we ignored two of our rate equations up here, right? We only used this one and this one. We ignored these first two because they deal with S, and we are going to assume that the S concentration isn't changing. That's one of the assumptions in the Michaelis-Menten law. And that's true only if we're early on in the reaction, so that the S hasn't had a chance to get depleted appreciably. So, I mean, it is getting used up and the concentration maybe is falling a little bit, but not enough to worry about. Then this assumption that the S concentration is constant is a decent one. On the other hand, if we're inside of a cell or any other biological being, usually the substrate concentrations are held constant by metabolism. Basically, the metabolism is there as sort of an external actor that deliberately holds, I mean, as the substrate is used up, the metabolism replaces the used up stuff with new stuff. And so in that case, the fact that the substrate concentration is constant is true, and deliberately true, held that way by the metabolism itself. On the other hand, sometimes in an experiment you can also deliberately set things up so as to hold the concentration constant if that's what you want to do. All right, a couple more important comments here. I said already, many enzymes obey Michaelis-Menten, or some slight variant on Michaelis-Menten. But the fact that something obeys Michaelis-Menten doesn't mean that it obeys this mechanism. This mechanism gives you Michaelis-Menten, but so do many other mechanisms. There's a huge number, probably an infinite number in truth, of mechanisms that all give the same rate law for how the rate of reaction or the production of product depends on the substrate concentration. I put a longer aside here in this, at this point, on this point, because I have some relationship to the people who did this work, and it's relatively recent, 10 years old. This is done by a couple of theorists working for a close collaborator of mine. And they were able to show straight out on paper, in a tremendously complicated derivation, that it is true that any unbranched mechanism, no matter how complicated, no matter how many steps it has, if for any such mechanism, anything in this whole large class of mechanisms, the Michaelis-Menten rate law is obeyed if and only if all the substrate binding steps in the mechanism, so the substrate binding step in the simple Michaelis-Menten is this one, right? That's a place where a substrate is being bound to form an enzyme-substrate complex. If all those substrate binding steps are separated from each other by an irreversible step, so something like this. Here's a binding step, here's a bunch of steps, one of which is a binding step, that's better to say. Here's another bunch of whole steps. So I just made this up out of the air because, as an example, but there's an irreversible step between this block of steps and this block of steps. And there are no irreversible steps right on the binding steps themselves. And therefore, this mechanism, however complicated it is, however different it is from the normal Michaelis-Menten mechanism, will still give rise to a Michaelis-Menten rate law. It will still obey the Michaelis-Menten kinetics. So it is really true. The Vmax and Km will have different definitions. This has got a bunch of different rate constants, right? 1, 2, 3, 4, 5, 6, 7 different rate constants. Michaelis-Menten only has 3. So Vmax and Km will be related to those rate constants in a much more complicated way, but there will be a Vmax, there will be a Km for some definition of them, and the Michaelis-Menten rate law will hold. All right. That's a bit of an aside that won't be on the exam. I haven't said nearly enough about it to be clear, so, but it hopefully keeps you alert that the fact that something obeys Michaelis-Menten doesn't mean it obeys the Michaelis-Menten mechanism. All right, what does the Michaelis-Menten rate law say? Here it is. V is equal to Vmax times 1 over 1 plus Km over the S concentration. If you plot that versus the S concentration, you get a curve like this. Notice that on the y-axis here, what I'm plotting is the velocity divided by Vmax. In other words, I've divided both sides here. So this is velocity over Vmax. And that's just 1 over 1 plus Km over S, which means that Vmax, if I divide the velocity, if I scale the velocity by Vmax, then Vmax doesn't appear on this side of the equation anymore at all. Notice also, I've scaled the x-axis by Km, and the only thing that ever appears on this side of the rate law is S divided by Km. In other words, if I wrote this as y is equal to 1 over 1 plus 1 over x, where x is equal to S over Km, then that curve, which is a pure mathematical curve, is universal for all Michaelis-Menten mechanisms. And that means this curve that we're looking at here is universal for all Michaelis-Menten mechanisms. The only thing that changes from one enzyme to another is the scale on the y-axis which is this Vmax, or the scale on the x-axis, which is this Km. So Vmax and Km just rescale the dependent variable and the independent variable, but otherwise this curve is a universal curve. And it's for that reason that Michaelis-Menten is so, I mean, it's for all the reasons I've been giving here. A huge number of enzymes obey the Michaelis-Menten law, and the Michaelis-Menten law is particularly simple. It has this universal curve except for scaling on the two axes, and a huge number of enzymes obey that. So the Michaelis-Menten mechanism is capable of categorizing and understanding a huge number of enzymes in a particularly simple way. That's the kind of theory that gets used very widely. And, you know, the Michaelis-Menten mechanism is really old, right? It's from 1913, originally 1925 in its current form. So that's almost 100 years ago. And still, it's almost universally used among the people who do these kinds of things. All right, so this is all just saying what I just said. I won't say it again. What about this shape? What this is saying is that as we increase the substrate concentration and we look at the velocity that we get, right? So this is the initial velocity, really. We start the reaction off, let it go for just a little while, and then you stop, measure the velocity as it goes, the rate of production of P as it goes. And then you stop the reaction before the substrate starts getting depleted, and then you change the initial substrate concentration again and repeat that, and in that way you create a bunch of data points, and if you plot those data points, you'll get a curve like this. Why is that? Why do you get a curve that starts out with a small velocity when you have small concentration of substrate, and then a large velocity when you have a large amount of substrate, but one that saturates out, right? That plateaus out. If you keep increasing the substrate concentration, eventually the reaction doesn't get any faster. You can increase the substrate concentration to the moon, and the reaction doesn't get any faster. Why that behavior? Well, it's because as you're increasing the substrate concentration, you're loading up the enzyme, right? So you put some substrate in. If you're at very low concentration of substrate, you form a little bit of enzyme-substrate complex, and then that goes on to form product, and that contributes to the Vmax here, but you don't form very much because you don't have enough substrate to really load that enzyme up. On the other hand, if you put a ton of substrate in, then you load this enzyme substrate up completely, and you can't go any faster than that, right? This enzyme substrate complex is now converting substrate to product and releasing it just as fast as it possibly can. Putting more substrate in just clogs up this part of the reaction. So it limits out over here. We're making the assumption that S can't go to P on its own, right? S has to have, in this model, S has to have the enzyme present in order to go. So that means that no matter how much S you put in, you don't get any P until you've put the enzyme in, but that means you need to have enzyme when you've loaded up all the enzyme that there is. With substrate, you can't go any faster. Also, what's the range of substrate concentrations where the enzyme starts to turn on and starts to approach that maximum? Well, it's Km. Km, remember, has units of molar, it has units of concentration, and that you can see, oops, I'm just eliminating all these pinks. You can see by the way well, I erased everything, but you can see by the Michaelis-Menten law that S, the substrate concentration, is scaled on Km at every point, which means that when S is equal to Km, if we go back up to our formula here, let's look at that. Long way up, here it is. If S is equal to Km, then this is a 1. And you've got 1 plus 1 in the denominator here, that's 1/2. And so when S is equal to Km, when the substrate concentration is equal to the Michaelis constant, then the velocity, the rate of reaction, is equal to half of Vmax. And if anything above that, if you go to substrate concentration higher than that, then you'll go faster than half. Anything lower than that, and you'll go slower than half. All right, back down. All right. Another parameter that's important is Vmax itself, of course, but Vmax is equal to K2, the second. So E plus S goes to ES, goes to E plus P. This is K2. It's the rate constant for the second step. This is the important quantity, right? The amount of enzyme you put in is going to vary from experiment or situation to situation. So let's divide Vmax by the amount, let's scale Vmax by the amount of enzyme that we put in. That quantity is just K2, and because that now determines the Vmax, that's the intrinsic part, the enzyme intrinsic part of Vmax, it's called Kcat usually. In a lot of presentations, they'll call this Kcat from the beginning. I called it K2. But a lot of people just call it Kcat right from the beginning. And Kcat is then called the turnover number. If you think about it a little bit, you can see that it's just the maximum rate at which a single fully saturated enzyme molecule converts S to P. It's sort of the intrinsic, it's the fastest possible rate. It's the Vmax, if you like, but for a single enzyme, a single saturated enzyme, rather than for a population of enzymes. Another quantity that gets bandied around a lot is the so-called catalytic efficiency. It's called eta here, Greek eta. That's Kcat divided by Km. I don't really know what the theoretical justification for this is. You know, I've seen lots of textbooks and other places where they talk about this catalytic efficiency. It's very widely used. And it has an interpretation. The interpretation is that when the number is large, when this eta is a large value, that means that every single substrate that binds eventually gets converted to product. You could have it the other way around, right? That a substrate binds and then just goes back, right? Releases again without forming product. Well, if this number is large, that means that the S's never get away, basically. Once they bind, they're going to go to product, and that's that. And so that's the way it's used. You know, it's kind of a, I don't know. I don't have much opinion of the catalytic efficiency, but it is widely used. You'll see it used. Lots of smart people use it, even though, well, I can dream up better numbers for that purpose. Anyway, it's widely used. Here are some numbers for actual enzymes. Yes, so some enzymes have large catalytic efficiencies. That means they convert every S they bind to a P. Some of them have relatively low catalytic efficiencies. That means a lot of the S's get away. They have to bind several times before they finally get converted to P. That's the significance of it. Here's some numbers for a range of possible enzymes. Here are the Km values. Remember, the Km values are sort of the turn-on values. How much substrate do you have to put in before the enzyme kind of turns on? Well, Km is the answer to that. And you can see that it varies quite a bit from from 100th of a molar down to 10 to the minus 6 molar, or micromolar quantities, also some millimolar values. Also the Kcat value, remember that's the sort of intrinsic enzyme production rate or turnover number, and that also varies a lot from quite slow, 1 every 2 seconds, or 2 every second really. No, 1 every 2 seconds, I take that back, to 400,000 per second for very fast enzymes. And then here's the efficiency number. You can see by the time you've gotten to these kinds of values that every single substrate that's binding is getting converted to product. Whereas for some of these lower numbers, probably a lot of substrates are getting away, and you have to get several bindings to occur before the chance occurs to create a product. All right, we will stop there. I think this lecture's gone on long enough. Next time we'll talk about Lineweaver-Burke plots.